Multiband topological group velocity control from slow light to light stopping.
Imagine a train that can travel both forward and backward in time, but only along specific tracks that twist around each other in a complex dance. That's the kind of wild ride we're stepping into with this Harper-Hofstadter model.
Whoa, I thought photonic lattices were already complicated. So what exactly does adding long-range couplings do here?
Think of the lattice as a city map where each intersection can talk to its neighbors directly, but also to those far away across the grid. By allowing distant chats, we open up entirely new routes for light to travel.
So instead of just slow down or speed up, you can actually change which directions are possible.
Exactly. The long-range connections create extra pathways that bypass the usual constraints of how light moves through a lattice. This lets us shape not only how fast light goes, but also whether it can loop around in one direction or another.
And what about those topological edge states? Are they still robust when you add all this long-range chatter?
They stay surprisingly tough. Even though the geometry gets more tangled, the system keeps its knack for protecting unidirectional flow at the edges, meaning light can circumnavigate defects without getting lost.
That sounds like a solid upgrade to any on-chip photonic circuit. But how do you actually control all these new connections in practice?
The researchers engineered it so the strength and direction of those long-range links can be dialed in using external fields or by tweaking nanoscale structures, much like tuning a radio to find just the right station.
I love how they turned abstract math into something you could actually build. But what happens if everything goes perfectly and light finally moves exactly as predicted?
Then we open doors to ultra-stable delay lines, robust quantum links, or even new kinds of optical logic where the directionality is as important as speed.
Well, this has definitely piqued my curiosity. I'm eager to hear how they tested all these ideas in their real hardware. Great question. When you remove all boundaries, you're testing how robust those edge states are when there's nothing to confine them. The team still calculates the eigenmodes of their finite-sized Hamiltonian, but now with infinite space on all sides. Think of it like taking a puzzle piece and letting it float freely instead of forcing it into a frame.
Exactly. They find that even without boundaries, the system retains its non-trivial topology, which means edge modes pop up in each bandgap, but only when the long-range coupling parameters meet certain thresholds. The numbers they report are tied directly to those parameters, like delta being 0.3 and eta vanishing entirely.
Interesting. And what does that mean for real-world transport?
It suggests that even in an idealized, boundary-less world, the edge states still behave as expected. They're not just artifacts of confinement, but intrinsic to the band structure itself.
So the edge states can travel freely without hitting a wall?
Right? They remain confined to their respective boundaries, but move in a way that's dictated by the sign of the bandgap churn number, basically telling them whether they spiral clockwise or counterclockwise around the system.
And how do they actually verify this? Do they simulate propagation or measure it directly?
They use coupled mode theory to model wave packet excitation and then track how those packets move under open boundary conditions. By choosing specific initial shapes, Gaussian pulses centered at certain positions, they can selectively excite either an upper or lower edge state.
Got it. So the simulation shows that if you fire up one edge mode, its partner on the opposite side moves in a coordinated fashion, and their direction matches what the churn number predicts.
Precisely. The clockwise modes circulate one way while counterclockwise ones go the other, matching the sign of their respective bandgap numbers.
That's pretty neat. Topology surviving even when you take away all boundaries. So what happens next? Do they test more parameter sets or look at how these edge states interact with bulk modes?
They probably dive deeper into those interactions, but the current work solidly establishes that open boundary conditions don't destroy edge behavior. Instead, they expose it in a cleaner form.
All right, Jamie, we just wrapped up some pretty abstract physics talk. Now this next part is all about how light behaves when it gets really slow, like almost stopping in these special edge states on a material's boundary.
Exactly. They calculated group velocity to see how quickly a packet of waves travels along the edges. By using the dispersion relation for these edge states, they found that in certain gaps where no normal modes exist, the edge states can travel without scattering.
So there are gaps? Like empty spaces in the spectrum?
Yes. They identified first, second, and third band gaps. In those gaps, only these special edge modes exist, and when they excited them at specific points along the edge, they saw clear clockwise or counterclockwise motion depending on which gap they were in.
So, if you imagine the lattice as a strip of material with a boundary, light can travel around that edge without bouncing back?
Pretty much. It's like having a one-way street for photons where they stay confined to the edge and keep going in one direction only.
And what's the point of figuring this out? Why care about light moving slowly at an edge?
Because controlling how light moves is key for things like optical switches, sensors, or even quantum information devices. If you can reliably guide light along edges without losing energy, that opens up new ways to design compact photonic circuits.
I love it when science gets practical. So they're basically mapping out a super efficient highway system for photons at the nanoscale?
Exactly. And by understanding how these edge modes behave in different gaps, they can start designing materials where light behaves exactly as needed, sometimes moving fast along straight paths, and sometimes curving around corners without reflection.
Sounds like a really clever way to manipulate light at tiny scales. I'm curious what happens if you try to make the lattice bigger or change its shape.
That's next up. They're already thinking about how altering the geometry could let them control not just speed, but also directionality and stability of these slow light channels.
Perfect. Jamie, I'm definitely going to need a cup of coffee after this brain workout. Alright, so we've been talking about how light can be slowed down and stopped using these topological edge states. Jamie, this next part is all about what happens when you push beyond a certain point in the band structure, specifically for values of delta between 0.32 and 0.65. What's going on there?
Exactly, Alex. When we look at that long-range coupling regime defined by 0.26 less than delta, less than or equal to 0.33, something really interesting happens with the way light moves through these edge states. Imagine you're watching a train traveling along a track. Normally it goes straight and fast, but if there are obstacles or curves, its speed changes.
So you're saying the light is like that train?
Perfect analogy. In this case, when delta falls into that range, instead of speeding up or slowing down smoothly, the group velocity, basically how fast the wave packet of light moves, becomes almost zero at certain points. Think of it as the train coming to a near stop before continuing on.
Wait, so if the speed is nearly zero, what happens to the light?
Well, that's where the ribbon band structure comes in. It shows us how energy levels are arranged for these edge states. In this regime, the first and third bands flatten out near delta equals 0.32, while the second band actually spreads out more, becoming less flat as we move away from the center.
Flatter sounds like a slower train ride?
Exactly. A flatter band means the energy changes very little, even with big shifts in momentum. For light traveling along these edges, this means it can get trapped or slowed dramatically without scattering off defects, like our train ignoring roadblocks on its track.
So you're saying defects don't bother the light much here?
Right? The flatness gives topological protection. It's like having a magically smooth rail that lets the train pass over bumps without jolting. We tested this by intentionally placing imperfections along the path, and yet the light kept moving forward almost undisturbed.
That sounds super useful for keeping signals stable in tricky environments.
Absolutely. This kind of robustness could help build better optical circuits or quantum information devices where you need precise control over light paths despite imperfections.
Wow, so this is about more than just theory. It's actually a step toward practical applications?
You got it. By carefully tuning delta and understanding how the bands behave, researchers can design systems that exploit these protected edge states for real-world tech.
And all of this hinges on those numbers, delta between 0.026 and 0.035, right?
Exactly. Those specific ranges define where the magic happens, the sweet spot for unidirectional slow light transport without loss.
So we're looking at a kind of Goldilocks zone in band structure space that enables this behavior.
Precisely, Alex. It's all about finding just the right conditions where physics cooperates to give us ultra-slow, topologically protected light movement.
Alright, so we're diving into this laser-written waveguide thing. What's the big deal about these photonic structures?
Think of it like building with light instead of bricks. They're creating these arrays where light travels in a super-controlled way by tweaking how it bends and shifts as it moves along.
Wait, so they're not just letting the light go straight? What's the point of making it bend helically or shift sideways?
Exactly. That periodic modulation, like twisting or stepping side to side, is their way of engineering how light interacts over time. It's similar to how you might arrange dominoes so they fall in a specific pattern, but with light waves.
Interesting. So this synthetic gauge field thing, what's that actually doing?
Imagine the light has an invisible magnetic influence along its path. This fake magnetic field changes how the light waves combine and interfere as they travel, creating conditions similar to a special quantum material called the IHH model.
The HH model, isn't that about two bands of energy interacting?
Right? It's like having two lanes on a highway where cars can switch between them in a controlled way. Here, the light's different states, bands, interact for practical devices where precise photon control happens without messy physical imperfections.
Okay, convinced now. But wait, how do they actually measure these effects?
They simulate band structures, observe light propagation in engineered lattices, then validate against model predictions, a digital twin approach before hardware experiments confirm concepts.
So testing builds confidence for real-world trials?
Yes, theoretical groundwork tells them exactly which signatures to hunt and how adjustments work if needed.
This isn't just a one-off trick, it's scalable.
Precisely. They're building a toolkit merging topology with engineering freedom for tailored designs like slow light devices or robust optical circuits.
Okay, stop being skeptical now. But hold on, if it works so well theoretically, why isn't everyone copying this already? Because photonic integration evolves slowly and scaling without losses remains tough. They've carved a path forward proving Floquet dynamics, plus auxiliary coupling deliver controlled, protected light transport.
Good idea. That paper's math and simulations make everything click together beautifully.
They added long-range connections between nodes like superhighways instead of local roads.
Right. These create topological band gaps, protected pathways where light travels without scattering, similar to tunnel systems that allow only certain directions.
The paper mentions central gaps and edge states with opposite chiralities.
Yep. They calculated twist per edge mode, clockwise spins versus counterclockwise ones, and showed under open boundaries bands 1, 3, or 2 carry protected edge light.
And tweaking the parameter.
They slow light until it stops, like hitting a speed limit at light speed. Simulations prove this survives defects because topology safeguards paths.
Oh, and there's this cool trick where they dial velocity to 0?
Exactly. By adjusting, they create light stop signs, freezing photons, then releasing them later. Super handy for buffering signals.
And all could be built using femtosecond laser-written waveguides.
Which means it's not just theory, it's a tangible platform waiting to happen. Imagine optical computers leveraging protected light highways with on-demand pause features.
So they're handing us blueprints for ultra-robust photonic circuits featuring built-in delay and stop capabilities?
Right. Like upgrading from regular roads to quantum-protected superhighways that speed things up or halt when needed.
Thanks for breaking it down, Jamie. The future of photonics just got exponentially more thrilling.
Anytime, Alex. Stay curious and keep asking those big questions.
That's all we have for today. Thanks for listening, everyone.
This has been Nano Insights. See you next time.